Okay, good morning everybody again. So yesterday we started this topic, the reaction mechanisms. So we were kind of halfway. So we started with hydrogen, oxidation of hydrogen. So here I think also so this is a kinetically controlled phenomena, the explosion limits. So we discussed this. And then oxidation of CO. And then we started with hydrocarbons. Okay. So simplest is the methane fuel, CH4. So saw there even for the simplest fuel there are many reactions involved. Okay. When they do the reduced mechanisms, as we were discussing yesterday, so this is like it has how many, the 277 or 325 reactions. So reduced mechanisms are, in 80s, 90s they were using two-step mechanism, 4-step, 8-step. There were 3 paths. One goes through, the main path you can say is CH2O, CHO, then CO. Then CO to CO2, that's pretty straightforward, simple. The other path was this going to CH2 and then CHO. The third path was this, CH3 gives you C2H6. So like reduced mechanisms, many of them didn't have this path. And what that meant, for certain conditions you'll get good results, for other conditions you may not get good results. Especially if you have, conditions where you have fuel-rich mixtures. Because what happens, fuel-rich mixtures you have, a lot more CH3, more fuel, right? So then this path was important, and people did not get good results. So reduced mechanisms, the point is that reduced mechanisms you have to be careful, what are the conditions if you use them, if you use a reduced mechanism. Any questions here? Okay. So this we discussed yesterday. Now we'll consider larger hydrocarbons. So now C2H6 we already discussed indirectly, right? So CH4 then C2H6 is part of this methane oxidation. And which is path 3. So what you produce C2H6, and then this is the common path to CO. So these reactions are called hydrogen abstraction reaction. That is, you remove one hydrogen radical. So you go from C2H6, you lose one hydrogen, so C2H5. And then C2H4, which is ethylene, and then C2H3, and then acetylene, and then you again hydrogen abstraction, and then there's a from C2H there are some other reactions which go to CO. So now this is for ethane, and then the other the larger hydrocarbon like propane, butane. So we'll consider those. So for these, the overall, the basic concept is very similar, whether it's a propane or it's decane. Decane, of course, there are some other reactions which will, what they will do is, you have a C10, right, decane. So it will produce, C9, C8. Then eventually it will produce, C3, C4. Then rest of the steps will be very similar. So there will be few steps extra if you go from, say propane to decane. So as you go to larger hydrocarbon, there is some few extra steps. Okay. So here we'll just discuss, propane, and I'll give some reference to like heptane. Okay. So basic steps are very similar. Now to understand this, okay, we have to know about the bond energy. Okay. So there is a CH bond. So mainly there are CC bond between C and C, and then bonds between C and H. Okay. And the bond energy depends upon also, okay, where these atoms are located. Okay. So if you look at this third or fourth line, okay. So if you consider propane, so let's draw propane. So propane okay. So you see there are a number of CC bonds. Basically, there are 3 CC bonds and number of CH bonds. Okay. So the CC bond, okay, energy is 80. Okay. So this is about 80. The units are kilocalorie per mole. Whereas CH bond is 98. Okay. So that tells you, which bond is more likely to break first when you start, heating up the mixture or provide conditions for reactions. Okay. So CC bond will break. So if this bond breaks, so you can say the propane plus M, then you can see what likely will happen. Okay. So this is less likely to happen initially, right? Because this requires CH bond, okay, breaking of CH bond. Okay. So if this bond breaks, then the path will be, so you can see this is C2, 1, 2, 3, 4, 5, C2H5 plus CH3. Okay. So that is commonly the initiation step for larger hydrocarbons. And same idea, you can extend to larger hydrocarbons, as I said. So if you have, okay, let's say, okay, butane. Because for propane, you can consider this, or you can consider this one. Outcome is same, right? Because there are only 3 carbons. But now if you have a larger one, so if you break this, okay, so what will you get? C3, so this is C4, H10. By the way, we are considering only alkanes here, okay, because there are so many different molecules, different fuels. Okay, so we can spend like the entire, 1 week on chemical kinetics. Okay, so now you have C4. So if you break this, so what you'll get? So I think this is probably C3H7, okay, and then CH3, right? Or you can break this, okay. So all of these can happen simultaneously, okay. It's not like any sequence or. Okay. So this one will give us C2H5 plus, I think C2H5 maybe, okay. This one will be very similar to the first one, okay. So this way you can do for butane, or if you have hexane or heptane. I think I've written some example of heptane. Yeah, so let me take this. So for heptane, so you can have C6H13 plus CH3. That means the first CC bond is broken. Or you can have C5 or C4. So that means if you have larger hydrocarbon, there are more intermediate hydrocarbon species which are produced. Okay. And this also tells you that if you already have a good mechanism, say for C6, which is hexane, then it's relatively easier to build for mechanism for C7. Okay. Because a lot of the reactions are already done there. Okay. A lot of reactions we already understand. Okay, so this is the first step, breaking of CC bond for larger hydrocarbons. Okay. Now there are more details like, okay, whether this bond should break first or this bond. There are some more finer details. We are skipping those details. Okay. So if you are interested, you can read more stuff. Oh, this is harder to read. Okay. So after the first step, okay, then then a CH bond is broken. Okay. So now you have C2H5 here. So C2H5 reacting with them. So now you break CH bond. So this gives you alkyls. Okay. Similarly, CH3 will give you CH2. And for heptane, I'm writing for both, propane and heptane. So heptane you had C6H13, so this will give you also alkyls, for larger alkyls. Okay, here is C2H4. Here you have C6H14, S12. You will have additional ones like C5H10 and so on. Okay, I'm just writing, so you can fill in the blanks and other alkyls. So that is the second step. Okay, breaking of CC bond, and then the hydrogen abstraction reactions. Okay. So again, what do we need for reaction to become very active? Radicals. So this gives us the radical H. Okay. And then this H can react with O2, because remember initially we had what? Fuel and oxygen. So H will react with O2, give us more radicals. Okay. So now you have the radical pool building up. Okay. So now these radicals, OH and OH, now they can react with the fuel directly. Okay. So that's the third step, or you can call the fourth step. Third step, you can just say, yeah, the radical pool. Then fourth is these radicals react with the fuel molecule. Okay. So when they react with the fuel molecule, then you get different. Mainly, you get the alkyls. Okay. So the way it is written in general. Here. So it is written as RH. So R for propane will be C3H7. Okay. So R is one H less. Okay. And if you react with H, it produces alkyl plus hydrogen. Okay. If it reacts with O, R plus OH. So basically, you are removing H, H atom from the fuel, or it can be with OH. Is there that then the reactions, which reactions will occur, becomes more temperature dependent. Okay. Because some bonds have more, require more energy for breaking. So primary CH bond has one C atom, so we can go back here to understand that. But more important thing is that if it's a flame, high temperature case, okay, then these differences are very, very small. Okay, so these are kind of finer details, the primary CH bond, secondary CH bond, tertiary CH bond. Okay. The primary CH bond has slightly higher, okay, or slightly lower bond energy compared to secondary and tertiary. So primary, okay, if you want to distinguish, will break a little bit earlier, require a little less energy compared to secondary and tertiary bond. Okay, so what is primary? CH bond, it has one C atom bonded with one C and 3 H atoms. Okay, so it's very clear with this example. So 3 H atoms and 1 C atom. Okay, so there are 3 primary bonds. This one, and this one. They're all primary bonds. Okay, and there are 3 here on this side. Okay, so there are 6 primary bonds. Okay, and either one can break. When we consider this reaction, because we have to remove H. So any of these H can come out, from the 6 bonds. And same thing applies to, larger hydrocarbon. Okay. What is the secondary bond? 1 C bond, 1 C atom bonded with 2 C and 2 H, which will be, okay, this one, right? So 2 C's, this and this. So these 2 are secondary CH bonds. Okay, because this C has 2 C bonds and 2 H bonds. Okay. And if you go to larger hydrocarbon, they will have more primary bonds and more secondary bonds, and some of them may have tertiary bonds. Propane doesn't have any tertiary bonds, okay, because it requires 3 carbons, 1 carbon with 3 other carbon and 1 hydrogen. More complicated molecules can have even, I don't know what is that called, like when you have 4, instead of 3 carbon, you have 4 carbon bonds and 1 hydrogen. Okay. So that can happen in more complex molecules. Okay. Any questions? So again, going through the steps. So first one is the breaking of CC bond. Okay. And if you have a larger molecule, then you have many CC bonds. Okay. And all are possible. So you produce these alkyls and alkenes. Okay. So you produce a lot of alkyls. Here like C6H13, C5H11. Okay. And then you get hydrogen from that. Next. Then hydrogen produces radicals. Okay. You remember this reaction for the hydrogen oxidation? Okay. So it produces radicals, and then the radicals react with the fuel and take out hydrogen. So the fuel undergoes hydrogen abstraction. Okay. So C3H7 will become, C3H8 will become C3H7. Okay. So that is how you can call it the major step through these 4 steps. Okay, that's the main outcome. Okay. All right. Then the next one, this is more details what we just talked about. So thus propane has 6 primary and 2 secondary CH bonds. So remember, these are all CH bonds. Whereas heptane will have 6 primary bonds, because, okay, 1 C and 3 H is only at the end, right? I think it's still, did I remove? I think I removed that. So only at the end you have 3 CH and 1 CC, right? So 6 primary bonds. But then it has many secondary bonds, 10 secondary bonds. If you write the formula for more complex molecule like 2-methylbutane, okay. So basically, butane, right? 4 carbons, then HH all around, right? Okay. Then you remove 1 H and add CH3, which is methyl. Methyl is CH3. So that's called. So and what this 2 means? Okay.
In the second carbon atom.
Exactly. Yeah. So you have C, 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 C. So on the second carbon atom, it could be second from left or right, but usually from left. Okay, so you remove H and you put CH3 there. Okay. So what that does, okay, now you have another CC bond there, right? Because you are putting CH3. So you have CH3, CH3, CH3. There are more CH3 now because you are adding CH3. Because larger, like if you take decane, how many CH3 you have?
2
Right? Propane has how many?
2.
2. Okay. Butane, hexane, they all have only 2. Others are CH2, CH2, CH2. Okay. Only at the end you have CH3 and CH3. Okay. So there are only 6 primary then. Okay. But the secondary will keep increasing as you go to larger and larger molecule. Okay. And then generally the secondary and tertiary bonds are relatively weaker. Also, I was saying the opposite. So they are actually weaker. And breaking of these bonds have lower activation energy. So the reactions involving these breaking of bonds, okay, have lower activation energy. As I said, however, at higher temperatures, they occur almost at the same rate. There is no distinction then, okay, between primary, secondary, tertiary. But you have to be aware of this. Then where this hydrogen is removed, okay, whether from here or from here, it may lead to different products. Okay, they are all like C3H7. Okay, but we have to distinguish between a normal, okay, propyl, which is C3H7, compared to isopropyl. So then their reactions are different. The rates are different. Like a good example is normal butane versus isobutane. Okay. Isobutane, okay, is much less reactive compared to normal butane. Okay. Like the gasoline is isobutane. Okay. If the gasoline was normal butane, you'll have big problem. The compression ratio will be like instead of 12 or 14, it will be like 5. Okay. So the reactivity depends on the actual then structure. Okay. So this one is much more reactive compared to iso. Okay. So fourth step, what is the outcome? You have lots of alkyls. Okay. If it is propane, then you have C3H7, which is an alkyl. Alkane, you remove one H, it becomes alkyl. Okay. So for example, C3H13, so this is for heptane. Okay. So the next step, these alkyl, okay, they will produce alkenes. Okay. So in general, so alkane is CN H2N plus 2, right? Okay, that is alkane, like propane, butane, and so on. So alkene means you remove one H, okay, like C7H13, so on. Okay, and so the next is the hydrogen abstraction reactions, okay, and also the breaking of CC bonds. Okay. So both of these are occurring now, breaking of CH bond and CC bond, once you have these alkyls. Okay. And which bonds are broken? Okay, this is a very well known. So to understand chemical kinetics, reaction mechanism, we have to understand this beta scission rule. Okay. And these are also called like beta bonds. So let's discuss this in some detail. Let me see how many are familiar with beta scission rule. Okay. Okay. So let's take this alkyl, propyl. Okay. So you remember where we are, like here on the fourth step, okay, you produce this R, which is alkyl, this is alkyl, okay. So you remove H. So once you remove this H, okay, then okay, this bond, and this bond, these three bonds become stronger. So the bonds which are broken now, okay, depending, they should be removed from this is called beta site. It's just beta site, they use a lot of Greek letters, okay. So you can read this. No, we are in the wrong slide. Next one. Okay. So the CH bond and CC bond, CH bond and the CC bond, okay, next to the radical site, okay, that's the radical site where H has been removed. Okay. Have bond energy 99 kilocalorie per mole, so about 100 calorie per mole. So lot more bond energy for this CC bond and CH bond. Okay. While the CH and CC bonds one place away, okay. So for example, this one or this one place away. Okay. Look at their bond energy, okay, much smaller. Okay. So we don't remember the actual numbers, basically. So bond energy of the CC bonds and CH bonds away from the beta site, okay, is much smaller. So that means either this bond will break or this bond will break, okay, or these bonds will break. These bonds also have more energy compared to bond energy compared to these. Okay. So more likely these will break.
Sir,
yeah.
One hydrogen atom is removed, then the bond energy reduces, because earlier you told that it is 80 kilocalorie and then 98.
No, when you remove this H, then these bond becomes stronger.
Okay, this is strong, but
Yeah.
this other bond energy,
They become weaker, yeah.
so
They
weaker
become.
means it is less than the earlier.
Yeah, yeah. There is some internal thing, the bond energy, how the levels of, yeah, exactly. That's a very good question. Yeah. Yeah, earlier, yeah, we were talking about the bond energy is
98
higher.
and 99,
Yeah,
98.
exactly. Yeah. Okay. So there is some kind of a, I don't know what is the word, maybe isomerization going on, internally. So, okay, so for example now, if this CC bond breaks, what do we get? Okay. So we are breaking this CC bond, so you'll get CH3. So now we have C3H7. So C3H7 will go to CH3 plus C2H4. So it will produce alkyl and alkene. So this is alkyl and this is alkene. Why I am saying that? Because for heptane you will have many alkyls and many alkenes. Okay. So if you break this bond, this is what you get. Or you can break this bond, this CH bond. So if you break CH bond, then what do you get? Then you will get C2. So we have 1, 2, 3, 4, 5, C2H4. So this also probably gives you similar product. Okay. Now there are other scenarios. So let's look at one or two more. Okay. So this is just one example. In step 5, okay, but going to step 4, what is step 4? Remember that you remove H to produce alkyl. So this is not the only alkyl, right? What about this one? So this is also alkyl. Okay. So there are several other possibilities. So this is just one example. So now what happens? Okay, this bond will be stronger, this bond will be stronger, this bond will be stronger. Okay. So now this CH bonds will break. So there are several different, okay, compounds which are formed during this step. So this is like the major step, you can say, in a way.
Sir, below,
Oh,
CH
here?
bond is broken, below, and CH bond is broken. Are we not getting a C2H4?
Yeah, this may be wrong. You can check that. Because basically what you are doing is, this is the situation, right? So we are breaking this bond.
CH bond.
Okay. So this bond is broken. So your H here, H here, H here, H here. So you have 4 H and 2 C.
C2H4.
C2H4.
One CH2 and then H.
Yeah.
CH2 and H.
Oh yeah, it will maybe probably CH2.
CH2
Yeah,
and
yeah.
H.
Yeah, you can balance that, number of carbons and number of hydrogen. Okay. So as we were saying, here now this H is missing. Okay. So now it will lead to different products, but it follows the same beta-Sijin rule. Okay. Now if you have heptane, then there are a lot more possibilities. So heptane means you have heptyl, which is C7H13. So C7H13, 7, we've got 6, 7. So without writing all the H, okay. So this is a beta bond here. So it makes this stronger, this stronger, this stronger. Okay. Or you can have H removed from here. Okay. So there are other possibilities. Okay. So if you really want to understand it fully, you can look at all these possibilities yourself and see what is the outcome. Okay. Oh, sorry. Yeah, you're right. Thank you. From C7H16 to C7H15. Yeah. Okay. So yeah, we can finish this example. So let's say this is the beta bond, beta-Sijin rule applied. Okay. So then this bond is stronger, this is stronger, this is stronger. Okay. So one away, this can break or this can break, right? So if this breaks, so here C7H15. So what is left here is C2, 1, 2, 3, 4, C2H4, and plus C5H11. And then there are several other possibilities, right? Because if H bonds, remove it from somewhere inside. I have to redraw this. Let's say this is the one. Okay. 3, 6, 7. So if this is the beta site, then this is strong, this is strong, this is strong. Okay. So maybe this will break. Okay. Then you can see what are the products formed. Okay. So for fifth step or the main step, so the CH and CC bond next to the radical site have bond energies higher. CH, CC bonds we have lower bond energy. So now you produce, okay, for heptane you produce, C2H4, okay, C5H11, okay, which is pentyl. You also produce this one, okay. So there are many others, as I said, okay. So, a lot of alkenes and alkenes and alkyls, or alkyls and alkenes. This is a tongue twister. Okay. And then the larger alkyl radicals like C7H13 or C5H11. Okay. So, larger alkyl radicals, they dissociate to smaller hydrocarbons, okay, going through beta scission reaction. Okay. So, this is the net result of that beta scission reaction. So, now you have olefins. Olefins are same as alkenes. Okay. For example, propane, what will be the propene? Okay. Propane is C3H8, so C3H6. Okay. So, C3H6, C2H4, okay, those are the two alkenes or olefins they are called. Okay. I think olefin is more of a like a commercial name, okay, where a scientific name is alkene. Okay. And if you have C7H16 heptane, then you can think of there are so many. Okay. So, C6H12, C5H10, C4H8, all of those are produced, okay, C3H6, and then a lot of alkyls, right, C5H11, C4H9, okay, C3H7. C3H7 was also produced for propane. Okay. So, once you have C3H7, the propane steps are relevant for heptane also. Okay. So, they build this mechanism okay, from bottom up. So, you have a mechanism for propane, then you can build it for butane, okay, because most of the hydrocarbons are same. Okay. Only you need initial few steps. So, you go to butane, which is C4. So, there will be what C4H9, which is extra compared to propane. Okay. So, that way you can build. So, now you have a lot of these olefins. Now, they go through the oxidation reactions, because now you have O there. So, for example, so it produces CH2O. Okay, it also produces other like C2H4, again CH2O. But remember, in methane also you had the CH2O. Okay. Then all the reactions involving CH2O become important. Okay. So, those you can take from methane or from smaller hydrocarbon oxidation mechanisms. Okay. So, eventually the system contains smaller hydrocarbons, okay, because larger ones are reduced through hydrogen abstraction or breaking of CC bond. Okay. And then then oxidation reactions. Oxidation reactions will be with O and OH. Okay. So, I did not write a lot of steps in step 6. So, now the system contains species that involve reactions of H2CO, CH4. Okay. C2H means whatever C2H3, C2H5. Okay. So, now then the CO oxidizes through to CO2 through CO oxidation reactions, which we discussed earlier. Okay. And this is the dominant step. Okay. Similarly, H2 will form H2O through oxidation steps of hydrogen. Okay. And H2O is produced in lot of steps. Whenever any hydrocarbon reacts with OH, okay, like say C3H7 reacts with OH, what it will produce? It will produce C3H6 plus H2O, because H is abstracted from the hydrocarbon and then combined with the OH, okay, to produce OH2O. Okay. So, H2O typically, when if you look at some flame structure, you will see H2O starts being produced earlier compared to CO2, okay, because it's produced through a lot of initial steps also. Whereas CO2, you need buildup of CO and then you produce CO2. Okay. So in future, whenever you look at any flame structure, whether it's turbulent or laminar, doesn't matter. Okay, you'll always see H2O starts increasing first compared to CO2. And same thing, CO starts increasing first compared to CO2. Okay. And this is also the way, to produce like the syngas. Okay. You take a larger hydrocarbon and take a very fuel-rich mixture, you just add a little bit of oxygen. Okay, with just a little bit of oxygen. Okay, and you control the temperature, of course. Okay, so then what will you produce? So if you understand, if we understand a little bit of chemistry, we can answer that very easily, because if you have a lot of fuel, there's not enough oxygen. So it's going to produce a lot of CO and H2, which is the syngas. Okay. So you do the incomplete oxidation of fuel by using just small amount of oxygen to produce the syngas. And then you can add some other species to control, how much hydrogen and how much CO. So you can control the composition of syngas. So this is called fuel reforming. Okay. So that is done through, so you have to understand these reactions for, not just for combustion of fuel, for reforming of fuel also. Any questions here? Okay. So this is just additional stuff. Now we discussed a lot of the steps. Okay. So during these steps, these intermediate hydrocarbons are produced, right? So people have studied these, the production of this intermediate through using different experimental setups. So this flow reactor has been commonly used for these kind of experiments to study this chemical kinetics. Okay. So what is a flow reactor? It's a long tube. Okay. So you have this fuel, air mixture flowing, then you control the conditions. Okay. So let's say you have this mixture coming at 1000 degree Kelvin or 500 degree Kelvin. Okay. So you control the temperature, equivalence ratio and pressure in the reactor. And then you have the measurement points, your sensors for temperature, for species. So you measure as a function of x. So you have a long tube, okay, and then you measure the composition and temperature as the mixture flows. So as this mixture is flowing, it will go through chemical reaction. So that way they can look at, how the chemical reactions are occurring in a way. Okay. Let me see, this is for propane. Okay, I've taken this from one of the books, I think it's probably Turns. Okay. There are a lot of figures like this you can find online, a lot of papers. So let's look at the overall thing. So here, equivalence ratio is extremely lean mixture. Okay. So at normal, like say room temperature or low temperatures, okay, this will take forever to react. Okay. So the initial temperature is about 1000 degree. Okay, so you heat up the mixture, so it's flowing at 1000 degree Kelvin. Okay. And since the equivalence ratio is so low, and your initial temperature is 0.12. Okay. So first of all, like the program we are using yesterday, we can use that program. So what will that program give us? Okay. It will give us the values at the end, not intermediate values. It only gives the final composition. Okay. And I think you're going to get that program. So as a practice, you can do this. For propane, take initial temperature 1000 degree and take phi 0.12 and see what are the final products and what is the temperature. And then you see the temperature will only go up like few degrees. Okay. So here it goes from 1000 degree to 1222. Okay. So that equilibrium program will give you the final values. Okay. So this is also very important, because what is equilibrium? That you give enough time to chemical reactions to occur. But we don't worry about chemical reaction, just the final product. Okay. So in in terms of combustion engineers language, we say we give enough residence time. Okay. So if the residence time is large enough, then we get the equilibrium properties. So that's the relevance of what we discussed so far last 2 days, the equilibrium properties. Okay. That the chemical time is not considered. So it's either it's 0 or it's infinite. Okay. Because if it is chemical time is 0, you put the mixture instantaneously, you will get final composition. Infinite, of course, it's the same thing. You get the final composition. Okay. So the equilibrium, you can check what are the properties. So at equilibrium, you will not have all of these intermediate species. Okay. You only have the major species. Okay. CO2, H2O, and so on. Okay, and some small amounts of CO, H2, and stuff like that. Anyway, so this is the properties are plotted as a distance from the left end of the tube. Okay. So this is already, so here it is 0 centimeter, maybe not 0. No, it's not 0, it's 25. So it starts from 25 centimeter. So first 25 centimeter, nothing is happening. It's very, very slow. Okay. Why it is very slow? Because there is very little fuel, lot of oxygen. Okay. So then, okay, somewhere around 60 centimeter, there is a typo here. Right? Yeah, I don't know how did that happen. This must be in the original paper. Okay. So this should be maybe 37. 37, yeah. Okay. So around 60, you see the temperature. So you see the fuel is being consumed, right? But temperature is not increasing at all until here. Okay. So this fuel is not giving you CO2 and H2O. Okay. What it is giving you, is indicated here. You see, it's giving you a lot of these intermediate hydrocarbons: C2H5, C3H6, CH4, all of these, which we just discussed today. Okay. And then other ones which are shown here in more detail. C2H, yeah, these are shown in more detail. And then you see, once you have these, then you start producing also C2H4O. Okay. Which was the, if I go back, C2H4 will be in the 6th step. Okay. Once you have C2H5, C2H4, then you have the oxidation. Okay. So you can see the evidence here. So CH2O, okay. So this is produced earlier, and then C2H4O later. And now let's look at CO. So CO starts here. Okay. And where is CO2? Okay. There is no CO2 here at 73 centimeter. CO starts here. CO2 starts here. Okay. When you have enough CO. Okay. And when CO really peaks, so this is like CO is being produced through all those reactions. Okay. And now what happened here? Okay. So now you can easily guess what reaction is taking, is doing this. Yeah, CO plus OH reaction. Okay. So CO plus OH reaction is now producing a lot of CO2. Okay. And where is H2O? Yeah, I didn't plot. So otherwise, the H2O will start much earlier than CO2. Okay.
Sir, this flow is taking place at what pressure?
I think it's atmospheric. Okay. This is one of the experiments, I think, of Dreyer. This reference is in the book. Okay. This is the reference for, I think, the publisher. This must be Combustion Science and Technology Journal. Okay. Now, I mean, I have no interest selling Chemkin, but if you do, Chemkin can produce these results. Okay. So when I'm teaching, sometimes we give a project to use Chemkin to produce these kind of results. Okay. Because you can understand a lot, when I'm teaching, there are so many species involved. Okay. A lot of things get lost, Okay. People start losing interest also, but when they do it themselves, okay, then they can appreciate, what's going on. So to study chemical kinetics, they use flow reactor, they use also constant volume reactor. Okay, there are other like shock tube. There are a lot of setups people use, but this is a very commonly used step. And there are several, few universities at least in US which are still using these flow reactors. Okay. Focus is on chemical kinetics. Okay, now this is a totally different result. Okay. Now, ignition of fuel air mixtures. Okay. So, in the second lecture, I'll talk about this, constant volume reactor or constant pressure reactor. Okay. So, there are a lot of data on ignition of different fuel. Okay. Ignition delay time. That's one of the most common properties when they study ignition. Okay. So, the hydrocarbons, the larger hydrocarbons like heptane, dodecane, especially these alkanes, larger alkanes, okay, they have this typical plot of ignition delay versus temperature. But temperature here is plotted 1 over temperature. 1000 is just for convenience. Okay. So basically it is 1 over temperature. So temperature is decreasing this way. Okay. So normally, if you take a fuel air mixture, okay, and you decrease the temperature, right, ignition delay will increase. That's the normal behavior. It will take longer to ignite. Okay. But there is a intermediate temperature around 800 degree where you decrease the temperature, ignition delay becomes lower. Okay. So this is a well-known phenomenon called the NTC, negative temperature coefficient region. Okay. Typically ignition delay, okay, as a function of temperature to the positive power, because increased, it's 1 over T. So 1 over T, okay, you increase the temperature, I should decrease the temperature. You decrease the temperature because this plot is decreasing the temperature. So there is a region where the ignition delay actually decreases as you decrease the temperature. It ignites faster at a lower temperature, okay, which is against the intuition, right? So this is totally kinetically controlled phenomena. Here the low temperature kinetics becomes very important. Okay. That at very low temperatures, you have a normal behavior that you decrease temperature, ignition delay increase, right? At very high temperature, same behavior, but intermediate temperatures around 700, 800, 900, okay, you get this NTC behavior. It's called our cool flame behavior. So now this has been studied a lot because this is definitely very important for diesel engine combustion, because the temperature in diesel engine when the ignition starts is around 900 degree 1000 degree. Okay. So there's a lot of data showing this behavior. So now there are mechanisms which will reproduce this this behavior. So this is a good example. Okay. And similar plots you can find, for a lot of different fuels, heptane, decane, dodecane. Okay. Not just alkanes, also for alkenes. Some of alkenes you can find this. Okay. On the other hand, hydrogen, CO, methane, they do not show this behavior. This is only associated with larger hydrocarbons. Okay. So if you do this for methane, you won't see this. Methane, how it will go? It will go straight up. Okay. Monotonically, it will be increasing. So now it has become kind of a very accepted thing, but what is the important thing? If you use a reaction mechanism for larger hydrocarbon, you have to show this behavior, otherwise that mechanism is no good. Okay. So especially if you download from somewhere, you have to check that, because usually they say that, okay, is it for low temperature chemistry also, okay, or is it only for high temperature chemistry? If it is only for high temperature chemistry, then it will not show this behavior. Okay. Are we? We are totally out of time. Okay. All right. Maybe next one will go a little less time. All right. Let's stop here.